Hi everybody, my name is Dr. Tyler Foster and I am here to teach you about the process of glycolysis. Now, many of you may have learned about glycolysis in undergraduate school, maybe a little bit in medical school or any post-professional degree. However, this video is going to be a good tutorial about kind of the basics of glycolysis. I'm going to make it as easy as possible for you. So let's go ahead and take a look here. You've probably seen one of these charts before. It takes a molecule of glucose, goes through all of the intermediates, and eventually spits out a pyruvate. So we'll break this down a little bit further. We'll kind of talk about why some of these arrows are one-sided, why some are double, why this kind of splits off into two. So we'll break down each step. So this might be a little bit longer of a video, but I hope to hit on all the important stuff that you really should know about the process of glycolysis. So, what are some of the goals of glycolysis? Well, we take one molecule of glucose and we're eventually going to turn that into two molecules of pyruvate. So, a glucose molecule, let's say you eat a sugar cookie or something like that. It's got tons of glucose, lots of sugar molecules. These glucose molecules are 6 carbon molecules. So, they'll have 6 carbons. I'm terrible at drawing, so please don't judge. So they'll have 6 carbons, not in this shape, but I'm just trying to draw it out representative. And pyruvate is going to be a 3 carbon molecule. So it'll have only 3 carbons, but we'll have 2 of these. So that's where all of our carbons are. Our carbons are going to stay the same. We're taking this 6 carbon molecule in the form of glucose, our sugar, and we're going to break it down into 2 3-carbon element or molecules of pyruvate. And then these will eventually go on and be fed into the TCA cycle. And then from the TCA cycle, some of the intermediates can be dropped off at the electron transport chain, and eventually our goal is to make energy. So our goal is to make energy. And also, what we want to do is we also want to make some intermediates. Now, what are these intermediates? Well, they're energy carriers. They're going to be molecules like NADH, NADPH, FADH2, stuff like this, where we're going to be storing electrons. We're going to be making these molecules that'll store electrons, store energy, and then that energy can be harnessed later on down the road in the electron transport chain to eventually make ATP. And then also some of these intermediates can be dropped off and used for other processes. So we're not only making energy, but we're also making some intermediates that can go and feed some other cycles if needed. So the main thing that I want you to remember is one molecule of glucose will eventually become 2 molecules of pyruvate. So now we can get to the bulk of the material. This is going to take a little bit of time, but I think it would be best to go through step by step and actually learn what's going on instead of just showing you a chart and say, go memorize this. So let's go through it step by step. Might take a little bit longer than it should, but I do think by the end of this, you'll have a really good idea of what's going on and also why it's going on. So to begin, we'll start off with one molecule of glucose. You take a sugar cookie, chomp it, you swallow it, it goes down to your stomach. The sugar, the glucose, gets absorbed into the bloodstream, and we're left at this stage. So we've got glucose. It's kind of traveling through our blood. Now, what good is that glucose just in our bloodstream? Well, it's not. So we take that molecule of glucose that's traveling, and it is going to encounter a cell. Glucose outside of a cell is useless. So this glucose will need to enter the cell. Once inside the cell, it can either stay there, but also it can leave at this point. Unmodified glucose can enter a cell just as easily as it can leave a cell. But glucose outside of a cell is useless. We don't want it out there. So how is this cell going to deal with that? Well, we're going to take a molecule of ATP. ATP is adenosine triphosphate. Tri meaning 3, phosphate groups. So it's going to have 3 phosphate groups. It's going to be an adenosine with 1 phosphate group, 2 phosphate groups, and 3 phosphate groups. So these are going to be high energy bonds. So we're going to store high energy phosphate groups and use this energy later on down the road. So how is the cell going to keep this glucose inside the cell? Well, we're going to use a molecule of ATP, cleave off one of these high energy phosphate groups, and attach it to the glucose. Hold on, wait a second. Didn't I just say that the point of glycolysis was to make energy? Right now we're using energy. Well, yeah, it's kind of like the stock market. You have to invest some energy to actually get a return on that investment. So right now we're going to invest a little energy in the form of ATP. We're going to attach a phosphate group to a glucose to trap it inside the cell, so that way it cannot leave. And then thus we can use that glucose later on and hopefully make some more energy than we invested. So our goal is to make energy here. So we take that molecule of glucose, and what we're going to do, let me use a different color here. We're going to add an ATP, use a phosphate group from the ATP, and create a glucose 6-phosphate. So now we have a glucose 6-phosphate molecule. Where does the 6 come in? Well, we have this glucose molecule at the 6th position, the 6th carbon position, we're going to add a phosphate group. So that's what glucose 6-phosphate means. We have a glucose molecule with 1 phosphate attached to it at the 6th position. Now we need a couple enzymes that are going to be doing that. There are going to be 2 enzymes that attach this phosphate group onto our glucose to trap it inside the cell. Hexokinase, and the second one is glucokinase. The difference between these two probably isn't the best time to get into it now. This is a basic glycolysis lecture. Maybe I'll throw up another video on the difference between hexokinase and glucokinase here in a bit. Just remember, for now, we have a molecule of glucose. We want to trap it inside the cell, so we need to cleave off a phosphate group using one of these enzymes and attach it to the glucose 6-phosphate. Awesome. So now we have a glucose 6-phosphate inside the cell. What do we need to do? Well, we need to modify it here to make it useful. We've invested some energy, but hopefully we'll get some more energy out down the road. So right now, we're going to use another enzyme called isomerase. To change this glucose 6-phosphate simply into a fructose 6-phosphate. Phosphate still at the 6th position, but now our glucose turned into a fructose. Minor change to our molecule here. And all of this change that we're going to do here is to hopefully modify this into getting out some ATP. Then also remember the end product is our pyruvate. So we'll take 1 molecule of glucose and get 2 pyruvates, and I'll talk about how that occurs. So once we've changed it into a fructose 6-phosphate, we're going to have another important step here where we also invest another ATP molecule. So notice how these are one-sided arrows. We're going to use the ATP, and this reaction will only go in the forward direction since we're using an ATP. Also, over here, we're going to invest in ATP, so we only have a one-sided direction arrow. Fructose 6-phosphate will only be changed into fructose 1,6-bisphosphate. Now, big name, big kind of complex name. It's a fructose molecule, that exact same one that we took up here. We added yet another phosphate group to it. So now there's a phosphate group, bis, meaning 2 phosphates. There's 1 phosphate at the 1 carbon position and 1 phosphate at the 6 carbon position. So now the enzyme that's needed to do this is going to be a very important one. It's phosphofructokinase 1, PFK1. phosphofructokinase 1 enzyme. So that's going to catalyze the reaction that uses an ATP molecule to use that phosphate group. It has to grab a phosphate from somewhere. It can't just make one up out of thin air, so it's going to use an ATP phosphate and attach it. So now we've got this really, really phosphate-loaded molecule, a really high energy molecule. This is going to be the rate-limiting step of glycolysis. The phosphofructokinase 1 enzyme is going to be the rate-limiting step. We're taking this kind of energized molecule and making it a really, really energized molecule. From here on out, we're done investing ATP. Our goal is to make energy, so let's stop putting it in. Let's actually make some from here on out. So this fructose 1,6-bisphosphate molecule can be broken down. It can be turned into a glyceraldehyde 3-phosphate. So glyceraldehyde 3-phosphate molecule. Or it can get turned into, I know it's going to get a little bit confusing here because of all the limited space, and I apologize for that, but or it could get turned into a dihydroxyacetone phosphate molecule. Dihydroxyacetone phosphate molecule, also called DHAP. And I'll just write that for short since we're limited on space here. Dihydroxyacetone phosphate molecule. What's the importance of this? Well, this dihydroxyacetone phosphate molecule can then go on and be used for other things, or it can then get turned into yet another molecule of glyceraldehyde 3-phosphate. So we're going to be making one molecule of this. So here's one of that, and we'll make one molecule of this from this fructose 6-bisphosphate molecule. 6 carbons. Now we're going to cleave that 6-carbon molecule into 2 3-carbon molecules. So dihydroxyacetone phosphate only has 3 carbons, and glyceraldehyde 3-phosphate only has 3 carbons. Well, what's the point of this? Well, if we take one molecule of DHAP and turn it into yet another molecule of glyceraldehyde 3-phosphate, we now have 2 molecules of this glyceraldehyde 3-phosphate, and we can continue our reaction. So let's go ahead and introduce some enzymes here. We have our fructose 1,6-bisphosphate. The enzyme that's going to be cleaving it into these 2 molecules is going to be called aldolase. And then an isomerase, not a very important enzyme needed to convert this DHAP into our glyceraldehyde 3-phosphate. So, what's the bottom line? We take this 6-carbon molecule that has lots of 2 phosphates attached to it, high energy. We're going to cleave it into 2 molecules that have 3 carbons each. So it's a 3-carbon molecule. Each one of these has its own phosphate group, and then eventually this DHAP will get converted into a glyceraldehyde 3-phosphate. So now we have 2 molecules of glyceraldehyde 3-phosphate. That's an important thing to remember. We can now convert this glyceraldehyde 3-phosphate molecule into a 1,3. Oops. Let's erase that there. We can convert that into a 1,3-bisphospho glycerate. Now, where did we get this extra phosphate group? Well, this extra phosphate group is going to be used from a free phosphate. We're not actually going to invest ATP this time. We're just going to grab a phosphate molecule that's lying around and thus create a glyceraldehyde 3-phosphate, now with 2 phosphate groups attached to it, so it's called a 1,3-bisphosphoglycerate. Now notice how this is going to be a double-headed arrow reaction. Actually, I should be doing this where we have 2 different directions that we could go. So this one is also the same. We could either keep that phosphate group onto it or remove it at will. no energy difference between the two of them, so it's a double-headed arrow. The reaction can proceed in both the forward and the backward direction. Now we do have an enzyme that's going to catalyze this reaction. It's going to be glyceraldehyde 3-phosphate dehydrogenase. So glyceraldehyde 3-phosphate dehydrogenase enzyme. And it's going to catalyze this forward or reverse reaction, depending on concentration gradients of the two. So now we have this 2-phosphate molecule. We have a phosphate at the 1 position and at the 3 position of this phosphoglycerate molecule. Now this is where we can actually start making some energy. So we're going to take this 1,3-bisphosphoglycerate and turn it into a 3-phosphoglycerate. What's so important about this? Well, we cleave off one of the phosphate groups, and in the meantime, we're going to convert an ADP, adenosine diphosphate, into an adenosine triphosphate. So we actually made an ATP in the process. We're going to take one of the phosphates off this molecule and transfer it to this ADP, thus giving us an ATP. So here we invested 1, here we invested 2. We're finally going to make an ATP at this point. Now the enzyme that's going to catalyze this reaction is going to be the enzyme phosphoglycerate kinase. Phosphoglycerate kinase. All right, so this is an important step. It's going to be only one of the steps that we make ATP, and looking at it, it should be a both-headed reaction. We only have a couple steps that are important that are only one directions. This is going to be one of those reactions that can go both ways. Now we've also got another reaction that can go both ways, where we can turn this 3-phosphoglycerate into simply just a 2-phosphoglycerate. We're prepping this molecule. Not a very important step. This is going to be the responsibility of a mutase enzyme. It's just going to transfer the phosphate group from the 3-carbon to the 2-carbon position. Not that important. We're prepping this molecule, though, for another important step. So what we're going to be doing is we're going to be taking this 2-phosphoglycerate molecule using the enzyme enolase. We're going to be making a molecule of PEP. PEP is short for phosphoenolpyruvate. I just fear I'm going to be running out of room here. So phosphoenolpyruvate is going to be our next important molecule of PEP. This molecule has 1 phosphate attached to it. So remember, we're taking this 2-phosphate molecule, taking one of those phosphates off of it and attaching it to an ADP to form a high-energy ATP. So we only have 1 phosphate left, and it's at the 3 position, now it's at the 2 position. We made a molecule of PEP, and now what we're going to be doing is we're going to be cashing in that last phosphate group. So we're going to have that's another 2-headed arrow. We're going to have a forward direction only reaction now. And this PEP is going to be turned into, finally, a pyruvate. So here is our end product right there. This is going to be an important enzyme. It's going to be pyruvate kinase. Pyruvate kinase. And in this step, I've already said we're going to be removing that last phosphate group, so we take an ADP molecule and convert it now into an ATP molecule. So here we invested 1 ATP, here we invested 2 ATP, we got 1 back, we got another back. So how come then glycolysis, how can we invest energy and get the same amount back? Well, we don't. The tricky part is we're going to run this reaction. So let me get a different color here. We're going to run this part of the reaction twice. And why twice? It's because this 6 carbon fructose 1,6-bisphosphate molecule, 6 carbons, is going to get broken down into 2 3-carbon molecules, 1 glyceraldehyde 3-phosphate and 1 DHAP. This DHAP is then going to be turned into a glyceraldehyde 3-phosphate. So now we have 2 of these. We're going to have 2 of these glyceraldehyde 3-phosphate molecules, and we're going to have to run this cycle twice. So since we run this cycle twice, we're going to get out 1,2 ATP, 3,4 ATP. So we invested 2 ATP. We invested 1 here and 1 up there. So we invested 2 ATP. And then we're going to get out, we're going to get 1, 2, 3, 4. Remember, this cycle goes twice. Since we have 2 molecules of glyceraldehyde 3-phosphate, we're going to run it once with 1 molecule of glyceraldehyde 3-phosphate. This DHAP gets converted, and we're going to run it yet again. So we're going to get 4 ATP out. Important to know. Now we're also going to get another molecule out. This is going to be an NADH molecule. We're going to get out 2 NADH molecules. Where do we get that out? Well, I neglected to mention, kind of on purpose, up here, let's get a different color. During the step of converting our glyceraldehyde 3-phosphate into a 1,3-bisphosphoglycerate, we're also going to take an NAD, which is an electron carrier that doesn't really have its electrons yet, and we're going to convert it into an NADH, and this is going to be a high energy electron carrier. This NADH can then go on to the electron transport chain and dump its electrons. That's how we make the bulk of our ATP, is through the electron transport chain. But we're kind of getting molecules to prep up and actually invest into the electron transport chain. So, invest, we get 2 ATP in, but out, we actually make a net profit of 2 ATP, but we also make, in the meantime, 2 molecules of NADH. We make 1 here when we run our glyceraldehyde 3-phosphate, and then we make another NADH molecule once we convert our DHAP into our glyceraldehyde 3-phosphate and run it again. So we actually make 2 molecules of this NADH. So that's an important thing to know. From here, we can take our pyruvate and feed it into our TCA cycle, or the Krebs cycle. Our TCA cycle is going to be a cycle, so it's a circle, and what it does is we're going to create some more NADH molecules. We make a little bit of ATP out of the process, and we also make another energy carrier, not NADH, but this time it'll be FADH2 in the TCA cycle. So our pyruvate is actually going to be 2 molecules of pyruvate. So let me write that up here. Out we get 4 ATP, 2 NADHs, and we're actually going to get 2 molecules of pyruvate. Because remember, we ran this cycle twice. So invest 1 ATP plus 1 glucose, and to get out we get 4 ATP, 2 NADH molecules, and 2 pyruvate molecules, which can then go on and crank the TCA cycle. So now that we've kind of gone through this beast of a chart with lots of arrows and mess, I'm going to close this off, and we're going to open up this nice neat chart, which hopefully you can now respect, where we take our glucose molecule, attach a phosphate group to it, kind of change it up a little, get it prepped, add another phosphate molecule to it, cut it in half. So here's one path, here's another path. Both are going to end up in the glyceraldehyde 3-phosphate section. We're going to crank this twice, and we'll end up with, we'll end up with 2 molecules of pyruvate from our 1 molecule of glucose. Hope you found this video useful. If you have any questions, be sure to ask any questions you may have. I appreciate feedback on these lectures. I plan on making a video about the hexokinase and glucokinase difference. Should be a nice short video. And then hopefully one more on the TCA cycle. Thanks for paying attention, and have a good day.